Okay, ladies and gentlemen, we're going to see if we can put everything together that we've been learning. Um, all of the smaller questions you've been answering where you need to convert from mass to moles or moles to mass or to calculate concentration, all of those come down to being able to do the type of question we're going to look at now, which is called a stoichiometry question. So stoichiometry refers to questions where we use the ratios that we find in a balanced chemical equation. We'll call those the molar ratios. So you can see here, like this is a methane to water is a 1-to-1 ratio. If you're going to use up one molecule of methane, you need one molecule of water. And then because this is a balanced chemical equation, we see that we make one molecule of hydrogen and one molecule of carbon monoxide. So the ratios here are all 1-to-1-to-1. If I use up two of these, then I need two of those, and so on. So we can use that ratio to solve problems. If we know how much we're starting with, if I tell you how much maybe methane you're beginning with, you can calculate out how much hydrogen gas you're going to make. Or if I say we want to make a certain amount of CO, carbon monoxide, you can figure out how much water you're going to need to be able to make that CO. So it's using ratios, using all of what those conversions are from moles to mass to concentration that we've been working on, and just putting it into a question pattern that gives you a way of answering it, okay? Now, before we get into a big question, let's just make sure we have, excuse me, a common understanding of what an equation actually means, right? So as I was saying, this, if you take one molecule of this, one molecule of methane, then when you need to react that, you're going to need one molecule of water. You're going to make one molecule of hydrogen gas and one molecule of CO gas from carbon monoxide. Right? But that ratio can be applied to anything. So if you have, let's say, 24 molecules, then you are going to need 24 water molecules. You're going to make 24 hydrogen molecules and 24 carbon monoxides. Okay, so dozens just gave us a way of counting. We know really 24 is 48 molecules. So if you're going to use up 48 molecules of methane gas, you're going to need 48 of this water, and then you're going to make 48 of each other ones. It's always a 1-to-1. Whatever happens to one of the reactions or products will happen to the other in this equation because the ratios are all 1-to-1-to-1. Right? So then we can do the same thing with moles. If I was to give you a certain number of moles, let's just say 3.5 moles, right away you know how much hydrogen you're going to make because it's a 1-to-1 relationship. So if I start with 3.5 moles of methane, I'm going to make 3.5 moles of hydrogen. And that's going to take 3.5 moles of water and also make 3.5 moles of carbon monoxide. So it's using that ratio. In this equation, it's a very simple ratio. It's 1-to-1. Yeah, you've balanced equations in the past, so you know that sometimes the numbers are not 1-to-1, but what we're using here is simply the coefficients, the numbers that were out front. And when we don't write one out front, we remember that means it's a 1. So whatever this number out front, that's your ratio. And we'll look at a couple of examples next where the ratios aren't all 1-to-1 and show you how to deal with that. But that's really what we want to be able to do. And once you have an answer in moles, then you can turn your answer into mass. So you could actually figure out how much you're going to make or how much you need to go and get. But you can't use mass in these ratios. These ratios are for one particle to one particle. So they don't work with mass because if you try to do this with mass, the ratio here is, well, methane has a mass of about 16 and water has a mass of about 18. So the ratio is 16 to 18, not 1-to-1. And even if we divide that out, that would be 8 to 9. It's not a 1-to-1 ratio when you're doing grams. So these ratios are not in grams. They have to be only in moles or in molecules or in numbers of particles. And then when we're done kind of moving from one that we know, so say we know how much methane we have, and we want to know how much hydrogen gas we're going to make. Once we're done moving that value in moles, we can then convert this using our formulas that we've been working with into a mass or into a concentration or into a volume. Okay? So it's really starting to use why we write balanced chemical equations to start with, to be able to calculate how much stuff we need and how much material are we going to make as a result of the equation. Okay, let's just review that very quickly here. So we're going to use the word stoichiometry basically to refer to this type of calculation where you're going to be given the mass of something. So you're going to be given a starting mass of one of the reactants or one of the products. Then you're going to use a molar ratio. So a molar ratio, that's just the coefficients in a balanced chemical equation. You're going to use those to find some other mass in the equation. And so we'll always be given something to start, and then we'll be able to figure out how much, well, if we were figuring out how much we were going to make, then we would be calculating out the yield. We would figure out how much are we going to make of that product. And so that's called the yield. So that's one of the things you could be asked to predict. So in this case, if we were to combine a known amount of hydrogen and oxygen, we could calculate how much water we're going to make when we react those two things together. Or we might, in this case, this is a combustion reaction. We're burning the hydrogen with some oxygen to get energy. It's important to know the ratio of how much hydrogen do I need compared to the amount of oxygen. That ratio, 2 to 1, is very important. If you mess up that ratio when you go to measure out your hydrogen and your oxygen, you get incomplete combustion. You get gas being wasted, or you get products being made that you don't want to be made. And if you have too much oxygen, again, you're not getting as much energy out of the equation as you could get if you had the perfect balance. So we can use this technique to figure out how much H2 and O2 we would need to put in a container to get the best explosion, the best combustion, to make the most amount of energy. And so that's what I mean by quantity of reactants needed. If I had a liter of hydrogen, how much oxygen would I need to be able to make the most energy that I could possibly make? Okay, so those are the kind of two questions we're going to take a look at. So let's just jump right in. We'll do two examples. This one is just an example in my lecture notes, and then I'll do a second one that comes from a practice set of questions that I'll post on the classroom. But let's do this one first. It says what quantity or what is potassium chloride is produced when 2.5 grams of potassium is reacted with an excess of chlorine. So there's another new word for us, excess. So let's just organize this information that they've given us, and I'll explain what excess means in a moment. So what they've done is they've given us some mass information. So what I do is under the balanced chemical equation, I make myself a little table. So I'm trying to organize my data underneath this balanced chemical equation. So I've been given a number for potassium. So I'm going to write down 2.50 grams right here because that's how much potassium I'm given. Under chlorine, it says I have an excess. All that means is I'm being given enough chlorine to use up all of the potassium. This won't run out before I've used all of this up. I've got more chlorine than I need. I have an excess of chlorine. So I'll be able to use up the whole 2.5 grams. And that's important to know because if we're going to calculate how much potassium chloride we make off this number, we need to make sure that all of this mass is used up when it gets turned into potassium chloride. So in this question, then, we're going to take that 2.5 grams that we're starting with, assume that we use it all up, and figure out how much of this are we going to make. Now, there's a ratio here of 2 to 2, which is also could be simplified to 1 to 1, but it's not going to make 2.5 grams over here. This is a ratio of particles. not of mass. So we actually have to do a little bit of work to make this happen. And so what we don't have is, well, we have a ratio. So I'm going to write down the ratio here. The ratio we have to solve our question is 2 to 2. And you could write down the 1 for chlorine. We're not going to need it, but of course it's a 1. So there's our ratio, 2 to 1 to 2. And we know that if we have 2 atoms of this, we're going to be able to make 2 molecules of that. So that ratio is important, but we don't have our number in atoms right now. We have it in mass. So we need to convert the mass into a usable number. And that usable number would be something in moles. So the next thing I put in my data statement is moles. Now I don't know any of the numbers for moles. I'm going to need to know the one for K. I'm going to need to know the one for KCl. But right now I don't know what those numbers are. All I have is a mass. But of course we know our relationship that moles, this is from the formulas we've been using, is equal to mass divided by molar mass. So this goes back to the conversions we were working on earlier. And so we can put another row down here, and we'll just call it molar mass. And we could look up the molar masses for the things that we want to know about in terms of moles. I'm not going to take any time to look up chlorines because I'm not using it in the question, but I am going to look up potassium, and I am going to look up potassium chloride, and we'll put those numbers here in our table. So the mass of potassium atom, a potassium atom, is 39.10, so 39.10 grams per mole. Now I know we don't have 1 mole, we have 2 moles, but we don't need to put that into the equation, into our math yet. What we're writing down here is just the molar mass, excuse me, of potassium. So that's how much does 1 mole of atoms weigh. And then potassium chloride, if you go through the process and add it up, it actually equals 74.55 grams per mole. And that's just for 1 mole of molecules. Again, I know there's a 2 here, but we don't use that when we calculate out the molar mass. The molar mass is always for 1 mole. Okay, so that's our data statement. We've got everything set up, our masses, our ratios, and our molar masses. What we're missing here is our moles. And what we'd like to find in the end is to be able to fill in this box over here. What mass of potassium chloride am I going to be able to make? So somehow we've got to move from this position here, 2.5 grams that we're starting with, over to how much we're going to make. So here, it's always the same 3 steps. The first step, turn your mass that you've been given into moles. That's step number 1, and we're going to fill in that blank there first. We're going to move that number from here over to here, and we're going to use the molar ratio. So in a minute, I'll show you how to do that. That's our second step. And the only reason we can go from here to here, because now we're in moles, we're in numbers of particles, and that's what the ratio tells us. It tells us the number of particles that would be in each spot. And then once you know number of particles, moles, and you know the molar mass, you can convert in a third equation, you can convert this back into mass. And so we can solve our problem here, and that'll be our third step, solving our problem. Okay, so those are the 3 things that we're going to need to do, and we're going to go through each one of those steps. So this takes 3 smaller equations, but if you set up your data that looks like this, and then you go through and you come up with a kind of a pathway to follow, you're doing 3 simple calculations that lead to a bigger calculation in the end. Okay, so let's start tracking some of this through, and we'll just see how it goes. So first thing I'm going to do is solve number 1. So number 1, I'm trying to get moles, and if we look in our formulas, we know that moles is equal to mass divided by molar mass, which is equal to 2.5 grams divided by the molar mass of potassium, which is 39.10 grams per mole. And then when we run that through our calculator, we get 0.064 moles. So that's how many moles of potassium we have, 0.064 moles of potassium. Okay, so that fills in this box here, number 1. Now we need to move it over here to box number 2 so we can figure out, okay, if we have this number of moles, 0.06 of potassium, how much potassium chloride? Now I'm going to show you a formula way to do it, even though I know this is fairly straightforward. If you have 2 of these, then you have 2 of those. And if you have 0.06 of these, then you have 0.06 of those. It's a 1-to-1 ratio. But if you're not sure what the number is, then this is how we're going to set it up. And if the ratio isn't quite simple enough just to be able to do it in your head, this is how we're going to do it. The best thing we can do is just set up another ratio, and we can use the information we've got in our table here to solve this. So what we're going to do is we're going to look in this column first, the potassium column, and we're going to write down the number that's in the ratio. So that's the 2, and we're going to put it over top of the moles that we have. So the number of moles. And so in the first column, the number in the ratio, or the coefficient is the other way to call it, that's a 2. And we figured out that it's going to be 0.064 moles in that first column. And we'd like to know what's going to happen over here in the second column, this one, how many moles are we going to make? So we can set up another term in this ratio. Well, the number here on top is 2, but we don't know how many of these we're going to have, so we can just put a variable in there now, like an x. And if we multiply this all out, we can solve this. So we go cross multiply, which says 2x equals 0.128, and then x equals 0.064. So we've proven mathematically what some of you probably were able to do in your head, that because this is 1-to-1 or 2-to-2, then if we have 0.064 moles of the first column, we have the equivalent amount in the second column. Now occasionally, and quite often actually, the ratio numbers here will not be the same. They will be like 3-to-5 or 4-to-7. And it gets a little harder just to do that in your head. And so that's how I would set it up. Set up a ratio of the coefficient number, or the ratio number from the equation, over the moles, fill in the 2 bits of data you know, and then set up another term that has a bit of data you're missing. Cross multiply, and you get 2x equals 0.128, and then solve that for x, and we get 0.064. Okay, so that's the new little bit in this particular bit of math that we're doing. Now finally, we were asked to find out how many moles of, let me just get some of these numbers out of the way. We were asked to find out how many moles of something we were given, what mass we were going to make in the end. So we have to solve for number 3, which is we need to know mass of potassium chloride. So that again goes right back to our formulas. We're going to do step number 3 here. Just grab a pen. In step number 3, we want to find mass. And if we look at our formula list, mass is equal to molar mass times the number of moles. So in this case, the molar mass, we calculated that out and put it in our data statement. You can see it at the top there, 74.55 grams per mole is our molar mass, and we have 0.064 moles of that material. And so we go 74.55 times 0.064, and we get 4.77 grams. 4.77 grams for. And then that's our answer. That's the number we were looking for. What mass of potassium chloride are we able to make if we start out with 0.2 or 2.5 grams of potassium and an excess of chlorine? Okay. So there's a lot to these. If you're overwhelmed, I understand. But we'll do another one together. I'll post another one in a separate video so you can take a break for a minute. If you want to come back and take a look at another example, I will put another example up from the homework. But it's a matter of taking your balanced chemical equation, gathering up all of your data. Once you have your data gathered up, you'll have a column where you can calculate moles. You move the moles to another column, and then you can turn that back into a mass. It's always going to be this: put together your data, 1, 2, 3, 1, 2, 3. It's always that same pattern, and it's always going to follow these three formulas in a row. But if you take some time first and you set up this pattern so that you know what steps you need to do, it makes the question that much easier to understand, that much easier to do. Okay, so I'll leave it there, and I will post another solution to some of the problems on the worksheet, and you can see how you're doing with those. Okay.